We present DNF-Avatar, a method for creating relightable and animatable avatar for real-time rendering by distilling neural fields. Given a monocular RGB video as input, we create a relightable avatar that can be animated under novel lighting conditions. Previous state-of-the-art works can recover the intrinsic properties from monocular video based on ray tracing. However, the rendering time of state-of-the-art relightable human avatars is still slow, taking several seconds to render a single frame. Some other recent works reconstruct relightable scenes using on 3D Gaussian splatting, which achieves real-time rendering, but it's only suitable for static scene. The goal of our work is to reconstruct animatable, relightable 3D human avatars that enable real-time rendering, given only a monocular video. Previous works require querying implicit field in canonical space for each physical property during rendering. Also, the time-consuming ray tracing-based physically based rendering requires tracing hundreds of secondary rays for each rendered pixel. Although these works can recover disentangled material properties that are physically plausible, they are hard to use in applications where real-time rendering is a concern. Based on the above observation, to accelerate the rendering speed, we propose to distill the knowledge from an implicit teacher model to a 2D Gaussian splatting-based explicit student model, to take advantage of fast rasterization of Gaussian splatting. We further replace the time-consuming ray tracing-based PBR with an approximated fast PBR pipeline. We take intrinsic avatar as our implicit teacher model. The teacher model warps the sampled points in observation space to canonical space via inverse LBS, and query the implicit field to obtain the intrinsic properties. The final image is rendered via Monte Carlo ray tracing. Our explicit student model is based on 2DGS. For the student model, we warp the point from canonical space to observation space by forward LBS. To achieve real-time shadowing effects, we propose novel precomputed part-wise occlusion probes to model the shadow. Then, with the precomputed environment mipmap, we adopt a fast approximated PBR to render the final image. Standard rendering losses are used to supervise our rendered images with ground truth images. We also employ image-based and point-based distillation loss to regularize the intrinsic properties stored in 2DGS. To further distill the inductive bias from the implicit teacher, we randomly sampled some driven poses to render distillation avatars to help the student model generalize well to out-of-distribution poses. For image-based distillation loss, we calculate the loss between the rasterized intrinsic properties map from 2DGS and the rendered ones from our teacher model in training views. For the point-based distillation loss, we query the implicit field from our teacher in canonical space for each Gaussian primitive as supervision signals to regularize both visible and occluded areas. The approximated PBR is derived from the standard surface-based rendering equation. To avoid expensive ray tracing during rendering, we take the visibility term out of integral, which becomes an ambient occlusion term. This term can be precomputed and stored into partwise occlusion probes. The Cook-Torrance BRDF is employed and the integral can be split into diffuse and specular part. We further employ split-sum approximation for the specular part. Note that all the integrals with red bounding boxes can be precomputed and stored in lookup tables. We precompute the ambient occlusion in the training stage. We first separate our 2DGS in canonical space into 9 parts based on the skinning weights of each Gaussian primitive. For each part, we uniformly sample 3D grid points around it. For each grid point, we precompute an occlusion probe via rasterizing. We further preconvolve the occlusion probes with the diffuse lobe to obtain the ambient occlusion for all possible directions. Finally, we convolve with spherical harmonics basis and store the resulting spherical harmonics coefficients. During rendering, we first warp each Gaussian primitive to canonical space of each part based on a partwise inverse LBS. For each part, we do a trilinear interpolation to obtain SH coefficients. We evaluate the SH function with the warped point normal to recover the partwise ambient occlusion. The partwise ambient occlusion values are multiplied together to get the final ambient occlusion value. We compare our method with our teacher model IA on the RANA dataset. IA tends to produce high-frequency noise in certain areas due to the utilization of instant NGP. Whereas our model successfully keeps meaningful wrinkles while discarding high-frequency noise during distillation. Also, the volumetric scattering-based teacher model may sample secondary rays inside the surface compared to a surface-based student model, leading to a darker shadowing effect. We further conduct qualitative comparisons on the real-world people snapshot dataset. We achieve an overall comparable rendering results with our teacher model while being real-time. Furthermore, our model even performs better under smooth lighting due to our preconvolved environment map producing less noise than Monte Carlo sampling. We also show the effectiveness of our proposed partwise occlusion probes, which enables fast and high-fidelity shadow modeling under novel poses. Here we show the intrinsic properties that are learned by our model. Finally, we show more results under novel pose and novel illuminations. To sum up, in this paper, we built a novel framework to create animatable and relightable avatar for real-time rendering based on an approximated PBR pipeline. We designed a knowledge distillation strategy between implicit neural field and explicit 2D for human avatar reconstruction. We proposed partwise occlusion probes that lead to fast and high-fidelity shadow modeling. Thanks for watching.